Okay, so let's get started since it's already 6:30. So hello everyone to the week 5 TS session of this course, Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. And so as usual, with respect to uh, with the same pattern as we followed in the previous weeks, we'll go over with a brief recap of the course contents of this week, followed by a short discussion session. And after that, we'll solve some sample problems and we'll also discuss the uh, assignment problems for week 3 session. So let's get started right away. So, one second. Yeah, week, so week 5's course contents primarily focused on the concepts of fluorescence spectroscopy. One second, I'll just check if recording has started. Yeah, recording has started. So yeah, so week 5's contents primarily focused on fluorescence spectroscopy, and we started with the basic concepts of how the process of fluorescence as a continuous spontaneous emission process and a stimulated emission process can be derived from quantum mechanical theories through time dependent perturbation theory, Einstein's phenomenological approach, and as well as Fermi's golden rule. So after getting expressions for spontaneous as well as stimulated emission, we went along the concepts of um, fluorescence as a molecular process in itself, how molecules can be preferentially excited along a specific axis while it's passing through a polarization filter, and how the result of that can be a preferential fluorescence emission along a specific axis. And we also saw some expressions with related to fluorescence, such as the probability of excitation of photons along a specific axis, as well as the fraction of excited molecules along a specific axis, how it depends upon the polarization angle, as well as the difference in angle between some different polarization axes. And in addition to that, we also saw a small example of how randomly oriented fluorescence molecules give an anisotropy of around zero point 0.4 when the molecules are present in a semi-glossy state, and which where the fluorescence happens after before rotational motion. And in addition to that, we also saw how the energy of a specific photon is split after interaction with light, and how the energy is split between the transition energy between electronic energy levels, vibration energy levels, rotation energy levels, as well as the nuclear spin energy levels. And we also saw the corresponding wave function expressions for those, and as well as the Hamiltonian operators for those. And we also got uh, in the towards the end of the lecture, we also got a short recap into the Jablonski diagram, which is presented in this slide, as you can see, where the Jablonski diagram describes almost all the optical phenomena which is happening to which can happen to a molecule after it's getting excited by light. So the initial process that can happen to a molecule after uh, observing light is absorption phenomena, and after that a lot of processes can happen which include your internal conversion as well as your vibrational relaxation across your different vibration energy levels. And following relaxation by vibrational relaxation, it can also undergo electronic transition to the lower ground state, which we call it as fluorescence. And sometimes, very rarely, it can also undergo another process called intersystem crossing, where it jumps from a singlet excited state to a triplet excited state. And from the triplet excited state, it undergoes a de-excitation to the emission to the ground singlet ground state, which process is called as phosphorescence. And we also saw the differences between fluorescence and phosphorescence, where the phosphorescence has a greater lifetime than fluorescence because of the forbidden spin transition, which requires it to have a longer lifetime. So, with respect to the recap, this are all the concepts that we learnt around this week. So, if no one has any questions with respect to this, we can move on to the sample problems. And uh, since I can see no one in the room as of now, I'll just directly jump onto the sample problems. So, the first problem is, in a frozen glassy state, what is the maximum theoretical value of fluorescence anisotropy for a randomly oriented population of fluorophores, assuming the absorption and emission dipoles are parallel? So, this concept we saw in the previous classes, where the absorption was around, where we assumed that absorption and emission dipoles are parallel, um, as well as the assumption that the population of fluorophores were randomly oriented along all the axes. So in that case, the anisotropy factor will be zero point 0.4. So moving on to the next question. According to the Jablonski diagram, the non-radiative transition from a singlet excited state to a triplet excited state is known as what process? And as we saw in the recap, the answer would be intersystem crossing. So, so intersystem crossing is a process by which a specific molecule can undergo a transition from your singlet excited state to a triplet excited state. And once that transition happens, the emission from a triplet excited state to a singlet ground state will be known as your phosphorescence phenomenon. So, question number 3, why is the lifetime of phosphorescence typically much longer than that of fluorescence? The options given are triplets are higher in energy than singlets. The transition from the triplet excited state to the singlet ground state is a spin forbidden and involves a change in multiplicity. Triplets undergo faster internal conversion, and phosphorescence only occurs in the gas phase. So, as discussed in the previous question, the answer would be option number B, which is the transition from the excited triplet state to the singlet ground state is a spin forbidden and involves a change in multiplicity. That's why the phosphorescence takes has a longer lifetime and takes much longer than that of a fluorescence. So if you see the lifetime of phosphorescence would be like almost 100 to 1000 times that of your fluorescence. So fourth one is a numerical problem. So in a specific fluorophore, the rate of radiative decay from singlet state to the uh, so all the processes that happen in the process of fluorescence is from the singlet excited state to the singlet ground state. So here we have defined three rate constants. One is the rate of radiative decay, Kr, which is 2 into 10 power 8, and the rate of internal conversion, which is 5 into 10 power 7, and the rate of intersystem crossing, which is 1.5 into 10 power 8. So the question here is to calculate the fluorescence quantum yield of this molecule. And I thought of making it as a transition, but I couldn't. Forgive me for that. So basically, how you calculate the fluorescence quantum yield is you calculate the ratio of your radiative decay to the sum of all the rates happening in the molecule that can happen within the molecule. So it will be the ratio of your radiative decay by the sum of your radiative decay internal conversion. Uh, yeah. So your radiative decay internal conversion rate and intersystem crossing rate. So it will be your 10 power 8 divided by 2 into 10 power 8, which is your radiative decay divided by the sum of all these decays, which is 2 into 10 power 8 plus 1.5 into 10 power 8 plus 5 into 10 power 7, which is basically 0.5 into 10 power 8. So I have added all these, and in the denominator you will have 4 into 10 power 8. So 10 power 8s will get cancelled. So 2 by 4 will be equal to 0.5. So your fluorescence quantum yield for this specific fluorophore will be 0.5. And the last question, last sample problem for this week, fluorescence intensity is directly proportional to all of the following except which option? So we have incident light intensity, quantum yield, solvent refractive index squared, and molar extinction coefficient. And as we all know, like uh, we saw in the previous last lecture, that your as your incident light intensity increases, your fluorescence intensity also increases, and your fluorescence intensity also depends on quantum yield as well as your molar extinction coefficient. So the only thing that doesn't depend on your fluorescence intensity doesn't depend on is your solvent refractive index squared. So I thought of initially having a doubt session, but since uh, no one is there in this room as of now, uh, I'll directly jump to discussing the previous week assignments problems. So later, when I upload this video in the YouTube channel, people can refer to the solutions and they can get back to me through the Google Groups classroom if they want to uh, address any specific doubts. So the first question is pretty theoretical. So in time-dependent perturbation theory, we express the Hamiltonian, which is h is equal to h naught plus h dash in this expression. So in this expression, which holds true. So the options are given as h dash and h naught do not necessarily have the same eigenfunction, though they share the same vector space. H naught is a strong function of h dash. H dash and h naught are mutually exclusive operators and their eigenfunctions are not related. H dash has the same eigenfunction with h naught. And the correct option here is option number 1, where h dash and h naught do not necessarily have the same eigenfunction, though they share the same vector space. So, question number 2 is, if spontaneous emission were not to be present, then what happens? So, these are the options which are given are the value of Boltzmann constant would be more to account for the resulting longer excited state life time. The rate of excitation would not be equal to the rate of de-excitation in the presence of light. The system would absorb light after some delay. The Maxwell-Boltzmann law would not be valid. And the correct option here would be that the Maxwell-Boltzmann law would not be valid. So the third question, in the class we derived the Beer-Lambert law starting from Fermi golden rule. However, one is a steady state measurement, which is the Beer-Lambert's law, while your Fermi golden rule gives the rate of transition, which is the number of transitions per unit time. Which of the following equivalents make it possible to relate this? And the options are your relation between length of the cell and interaction time, your uncertainty principle involving energy and time, the length of the cell with density of states, and density of states with molar concentration. And we might have learned from week 3's lectures that the thing which holds both of them true, Fermi's golden rule as well as Beer-Lambert law, is the length of the cell and interaction time. So that will be the correct answer. So this is a bit of a tricky question. So the plot of number of absorbed photons against the concentration of the solution will be what? So the options are linear with molar extinction, linear with molar extinction coefficient determining the slope, exponential decay with molar extinction coefficient determining the slope, exponential rise with molar extinction coefficient determining the rate, and inverse exponential 1 minus e power minus kx with molar extinction coefficient determining the rate constant. Which one of them? Which one of them will hold true? So it's a bit tricky question because many people will think that the as the number of absorbed photons will like as the concentration of the solution increases, your number of absorbed photons will also increase. But technically, you have to think it from the initial expression of Beer-Lambert law, which is your which in which your absorbed intensity of your absorbed photons is dependent on your incident amount of photons through the expression of through a relation of 1 minus e power minus alpha cx, where your alpha is your extinction coefficient, x is your path length, and c is your concentration. So basically your um, basically your as your concentration increases, it will be a inverse exponential where it will be dependent on 1 minus e power minus kx. So that will be your correct answer. Option number D. And it's a continuation of the previous question. In the above experiment, if we plot incident intensity against the transmitted intensity, the plot will be what? And this is kind of a direct question because now it will be a straight line with a positive slope, because as your incident intensity increases, your transmitted intensity will also be increasing. So the next question is some multiple select question, so meaning that more than one option is correct. So the density of states as postulated by Fermi in Fermi's golden rule is due to what? So the options given here are mathematical convenience of treating the probabilities. Second option is light sources have finite spread and want to account for it. The energy levels of an ensemble of molecules vary due to collisions and hence to account for it. It converts the rate of transition to absorbance. And the correct options here will be option number 2 and 3. Just light sources have a finite spread and finite bandwidth, and the energy levels of the ensemble of molecules vary due to collisions. So, seventh question is your time dependent perturbation theory assumes what? So, there are four options here. One is with respect to your Hamiltonian operator and your wave function and your eigenstate vector. The second one is your interaction with light does not alter the potential energy of the system. And the third option is which your perturbation Hamiltonian is greater than your initial unperturbed Hamiltonian, so that H naught can be ignored. And the fourth option is time dependent nature of the perturbation is captured in the mixing coefficients of superposition. And we all know that the perturbation Hamiltonian is kind of time dependent because it depends on the time in which your light hits your incident photons. So that is the fundamental basis of your time dependent perturbation theory. So the correct option will be option number D, where your time dependent nature of the perturbation is captured in the mixing coefficients of superposition. So the eighth question is the value of uh, bra vector EF, H naught and ket vector EI, where uh, ket vector ENs is form the energy again based of Hamiltonian, the initial Hamiltonian. And this is a pretty theoretical question. Then the answer is option number 4, which is the value is an into d of ij, where an is a scalar constant and d of ij tends to 1 for I is equal to j and 0 for all of this. The ninth question is, given the rate of spontaneous decay is 2 nanoseconds, estimate the fraction of the molecule that will remain after 1 nanosecond and 3 nanoseconds. So given the rate of spontaneous decay is 2 nanoseconds, estimate the fraction of the molecule that will remain after 1 nanosecond and 3 nanoseconds. So this we saw an expression in week 3's classes where we can relate the number of photons after time t with respect to the fluorescence lifetime of the molecule, where your n of t divided by n naught is equal to e power minus t by tau, where tau is your lifetime and t is the time of your choice. So if you substitute here, in this case, if you substitute tau is equal to 2 nanoseconds, and then if you substitute, basically you have to find n of t by n naught at 1 nanosecond and 3 nanoseconds. And you already know that your tau is 2 nanoseconds. So you just substitute your t with 1 nanosecond and 3 nanoseconds, and you will get the answer as exponential of minus 1 by 2 and exponential of minus 3 by 2. That will be your fraction of molecules that will remain after 1 nanosecond and 3 nanoseconds. And so the next question, given the molar extinction coefficient of uh, given the molar extinction coefficient at 473 nanometer is 70,000 per mole per centimeter, estimate the amount of light that will be transmitted by a 1 micromolar solution in a 1 centimeter cell when 1 milliwatt of 473 nanometer light is incident on a cell. And we should give the answer in milliwatt. So basically, we have the epsilon value. We also have the constant. So we have the epsilon value here, which is 70,000 per mole per centimeter. We also have the concentration in micromolar, and we have the path length in 1 centimeter. So basically, what we have to find out is we have to find out the uh, exponential coefficient in this Beer-Lambert law, where you already know that your uh, in Beer-Lambert law, you know that your transmitted light is equal to the incident light multiplied by e power minus epsilon into CL, where epsilon is your this thing. So if you plug in all the values, 70,000 per mole per centimeter, 1 micromolar, you have to convert it into molar, which is 1 into 10 power minus 6 molar, and 1 centimeter is the path length because you can get the centimeter units cancelled. So if you put all of them, and you will, and we also have I naught as 1 milliwatt. So you just substitute 1 milliwatt here, and since they want the answer in milliwatt, you don't need to give any changes to the SI unit. So we just need to find out what is e power minus 70,000 into 1 into 10 power minus 6 into 1 centimeter, and that will give you the answer as 0.93 milliwatt. Approximately it will give you the answer in 0.93 milliwatt. So any answer between 0.92 and 0.94 milliwatt would be considered as correct. So I'll move on to the next question. So which is a continuation of the previous problem. In the previous problem, what is the possible maximum amount of time that the light interacted with that of the molecule? Give the answer in picoseconds. And the answer is any answer with respect to 33 and 33.3 will be the right answer. So the next question, if a fluorophore has two pathways originating from two excited states and both paths were spontaneous, say fluorescence and phosphorescence, with one of them having a lifetime of 10 power minus 4 seconds, it's in the order of nanoseconds, and 10 power minus 3 seconds, then calculate the maximum number of ground state to excited state transitions that can be made per unit time. So they are asking for the number of transitions per unit time. So what you have to basically do is you have to convert the uh, lifetime, which is in seconds, into rates. So if you do that, you will arrive at the rate of the rate of one of the the rate of one of the pathway will be 1 by 10 power minus 4, which will be 10 power 4 10 power 4 transitions per second, and other one will be 10 power 3 transitions per second. So per second, the number of transitions that can happen is 10 power 4 plus 10 power 3, which is like 10,000 plus 1,000, which is your 11,000 transitions. And this is a similar question, and they are asking that if in the same system, if we add a state such that for every 10 molecules that undergo phosphorescence, one molecule decays to this different irreversible dark ground state, estimate the maximum number of fluorescent decays that a given molecule can undergo before becoming dark. So from this 10 power minus 4 and 10 power 3, you can see that for every one molecule which undergoes phosphorescence, 10 molecules undergo fluorescence roughly. So the number of uh, maximum number of fluorescent decays that a molecule can undergo will be the sum of what phosphorescent molecules plus number of fluorescent molecules. So it will be 10 plus 10 into 10, which will be 110. So the next question, one OD absorbing solution transmits dash percentage of light. You have to give the answer in percentage. So for this, how we can solve this is, so we know that absorbance is minus log of transmittance. So to find the transmittance, you have to take the uh, anti-log of your negative power of the absorbance. So which will be 10 to the power minus 1, which will be 0.1. 0.1 is the transmittance, but they're asking transmittance in percentage. So 0.1 means it is almost transmitting 10 percentage of the total light, which is being directed towards it. So the answer will be 10%. And the last question is 50% transmission when expressed in optical density corresponds to what? So this is the same thing. So you apply the same formula. Absorbance is equal to uh, log of absorbance is equal to minus log of 0.5, and you will get the answer as if you get any answer between 0.3 and 0.33, your answer will be correct. Okay, we have one more question. So, which one will have higher absorbance, maxing to 1 cubic centimeter solutions in 1 centimeter path length cell that have one OD, or placing them one behind the other? So, which one will have higher absorbance, mixing to 1 cubic centimeter solutions in 1 centimeter path length uh, that have one OD, or placing them one behind the other? So, the answer will be uh, one behind the other, because you are adding the path lengths, which will result in more absorbance. So that's all the uh, sample problems as well as the previous week's assignment questions for this week. So uh, time so we have time till 8:30, so I'll leave the room for the doubt session. So if any of you have any doubts, you can clear it now. Else we'll meet for week 6 section, which is on 1st March from 3 p.m. to 5 p.m. So if no one has any doubts, we'll meet again on 1st March coming Sunday from 3 p.m. to 5 p.m. Thank you.